Hi guys, Mr. Rocco here. Hope you're having a great weekend. We're going to start a new topic this week, rocks and minerals. So the first part of the unit is on minerals. So that's what this video will be about. You should take out your reference table, your ESRT, and go to the back page, page 16. So when I refer to that during the video, you can look along with me. The whole back of the ESRT is all about minerals. So this is the definition of a mineral, or the 5 characteristics of a mineral. A mineral has to have these 5 things in order to be classified as a mineral. It has to be naturally occurring, which means it cannot be man-made. So they have to find it in the earth. It has to be solid, not liquid, not gas. It has to have a definite chemical composition. That means it's made of certain elements, things like carbon, oxygen, hydrogen, Fe is iron, Na is sodium, K is potassium, and there's obviously others, but these are just an example of some of the elements that are made up of in minerals. So that's what they mean by definite chemical composition, made of certain elements. Those elements, those atoms, carbons and oxygens, have to be arranged in a specific pattern. They're called crystal shapes, and I'll go over that as well. And the 5th thing is minerals have to be inorganic, which means they cannot come from things that were once living, right? Something that's organic means it came from something dead, decaying material, plant remains, animal remains. Minerals can't be organic, so they are inorganic. So again, they have to be naturally occurring, which means not man-made, solid, made up of certain composition of elements. Those elements are in a certain pattern, and inorganic. And you would think, well, there might not be that many minerals out there because that's a lot of criteria to be a mineral. But minerals are actually, there's well over 3,000, and they find new ones, rare exotic ones every year, 10 to 12 a lot of times each year on average are discovered each year. This is actually in my classroom. If you look over on the rock wall, the brick wall to the one side of my classroom, I have this really cool poster which shows just a sample of some minerals. I think there's a little over 150 on here if you count them. Minerals are usually put into different groups based on the most dominant element that's in them, and it's hard to see in this poster, but for example, all of these minerals down here, this bottom 3 rows, and you can see this again if you look at it in my classroom, these are called the silicates, which the silicates happen to be the biggest group of minerals. Silicates are made of 2 elements that have to be in them, and that's silicon and oxygen. And so if a mineral has silicon and oxygen in it, it's called a silicate. And there's a lot of silicates. If you look on the back of your ESRT, they list the composition. One of the columns, it's toward the right next to the name of the mineral. And if you look, almost, I believe, half the minerals listed on the back of your ESRT are silicates. Things like quartz. Quartz is obviously a very common mineral that has silicon and oxygen in it. Then above that, right here, are what are called the carbonates. Carbonates have to have, obviously you hear the word carbon, so they have to have carbon in them. Then you have up here the sulfates and the sulfides. They're going to have sulfur in them. Up here in this corner are the oxides, so they're going to have oxygen in them. All right, so you get the idea. Minerals are put into specific groups, but the biggest group are down here, which are called the silicates. Again, this is only a small sample of them, but these are all in the same family as quartz. They have silicon and oxygen. On the front of your ESRT, on page 1, they list the chemical composition for 3 different parts of the Earth, right? They list the crust, they list the hydrosphere, which is water, and they list the troposphere, which is the air, the lowest layer of the atmosphere. And again, the air you breathe is 78% nitrogen and 21% oxygen. Water, right, H2O. So you have 66% to 33% H2O, 2 parts hydrogen to 1 part oxygen. Then you have your crust. Crust is broken down by mass, which is how much of it, and volume is how much space it takes up. And you can see the first four elements alone, oxygen, silicon, aluminum, and iron, right there you're talking, probably about 75%. A big chunk of the Earth is made up of just these four. 99% of the crust is made up of the top 8. So oxygen, silicon, aluminum, iron, and then you're going to throw in calcium, sodium, magnesium, potassium. So just those 8 elements make up 99% of the crust by mass. And again, as I mentioned in that poster on the last slide, oxygen and silicon are the biggest group of minerals. They're called the silicates because you can see right there, about 75% is just oxygen silicon. It's 46.4% and 28.5%. So that's a huge part of the Earth's crust. And that's why quartz is very common. If you were to go outside your house and take a walk and just look for a rock and then pick up a rock, there's a very good chance that in that rock, quartz is in that rock. And it wouldn't take you that long to find quartz outside your house. Now, minerals are identified by 2 ways, chemically and physically. Chemically is where you're going to look at the elements, like we talked about. Does it have carbon? Does it have oxygen, hydrogen, sodium, aluminum, etc.? And then, again, the chemical composition is listed on the back of your ESRT. It's the physical properties or physical tests. Those are the ones, and again, you probably did this in middle school, where you're going to use those physical properties to help you identify a mineral correctly. So again, oxygen, silicon, aluminum, iron make up 88%, just those top 4. Again, there's over 3,000 minerals out there. 95% of the crust, the rocks on the Earth, 95% are made up of the 20 most common minerals, which are the ones listed on the back of your ESRT. Quartz, hematite, sulfur, talc, galena, pyroxene, etc. So if you look at those minerals listed on the back, those are the most common rock-forming minerals. Now, most minerals are what are called compounds. A compound means it's made up of more than one element. Again, quartz is an example of a compound. It's made up of the element silicon plus 2 oxygens, SiO2. So because it's made of silicon and oxygen, it's a compound. So anytime a mineral is made of more than one element, it's a compound. Salt, which is halite. Halite is the mineral. Salt is used, obviously, for everything from melting the snow and ice on the roads to the salt that you put on your French fries. And so that's made up of sodium, Na, and chlorine. And so you take the sodium and chlorine, those 2 elements together, and that's now makes it a compound. So if it's made up of more than one, and some are made up of way more than that, again, look on the back of your ESRT, you'll see some minerals have, 6, 8 different elements that are in it. But as long as it's made of more than one element, it's a compound, which is going to be most of your minerals. Now, the ones that are only made of one element are not only an element, they're called an element, and they're listed on the periodic table of elements, but they are also what's called a native mineral. So a native mineral is made of just one element and is an element. And these are 4 examples. Gold. Gold is on the periodic table. Its abbreviation is Au. So gold is an element and gold is a mineral, right? You can find gold in the earth naturally. Same thing with silver, Ag, copper, Cu. And then comes carbon. Now, carbon is on the periodic table. Carbon is the only element in 2 very different minerals, which I always find this fascinating, graphite and diamond. And they are on opposite sides of the hardness scale, which we'll talk about here in a little bit. So graphite is very, very, very soft. On the hardness scale, it's given a value of a 1. Diamond is on the other side of the hardness scale, extremely hard, and that's a 10. And it's very interesting that they're both made of carbon atoms, graphites and diamonds, but one element is very soft, a 1, and the other one is extremely hard, a 10. And it's really, because say, well, why? Why does that happen? It's how the atoms are arranged. The way the atomic structure, they call that, how those atoms are set up, the pattern internally affects hardness. It affects other things too. Besides hardness, it affects the shape, how the mineral breaks, etc. And the reason is, in a graphite, just to kind of keep it short here, graphite, the carbon atoms, I should say, in a graphite are all arranged in thin sheets. And so graphite's in your pencil, right? So if you're writing with a pencil, what happens is those sheets just break off very easily. The bonds break between the sheets, and these sheets will just break one at a time as you're writing on a piece of paper. Whereas a diamond, the atoms are really tightly packed together, the carbon atoms. And so those carbons in a diamond are extremely bonded together, so strong that, again, it's very hard to break them. So it's always fascinating that you have the same element in graphite and diamond, yet one is soft and one is really hard. But again, it's how those atoms are arranged. So all of these, gold, silver, copper, graphite, diamond, they're all called native minerals, made of only just one element. And sulfur. So sulfur is on the back of your reference table. Again, it would just be S, made of sulfur. So sulfur is an element, and sulfur is a mineral. Sulfur usually has, it's hard to see in this picture, like a yellowish look. Again, you probably were exposed to these minerals when you did minerals in middle school. Sulfur has a rotten egg smell to it. Some people have sulfur water. If you turn on the tap in your house and you have this sulfur, and that's when they drill for a well, as we talked about last week, drilling for a well, they will hit a sulfur deposit sometimes underground, and then that sulfur gets mixed into the into your drinking water. You can put a water filtration system in to get rid of that sulfur. It's not going to necessarily hurt you. It just has that horrible rotten egg smell. So physically, these are where you're going to look at the mineral based on its physical properties, or what I call the physical tests. And so let's go through these physical properties. Some of these properties are helpful. They're good tests. They help you identify the mineral easily. Other tests are not as good. And I'll kind of point them out as I go through them here. So take the first physical property, color. Color is not a good way to identify a mineral. Now, most minerals have common colors. And if you look on the back of your ESRT, there is a column, it's toward the left-hand side, that'll say common colors. So minerals do come in sometimes the most common colors, but some minerals will come in many colors. And if you look at a lot of those minerals on the back of your ESRT, they'll use the word variable, right? Variable means it comes in a whole slew of colors. And so many of those minerals, if you look at the back of that reference table, will say that. They'll say variable. For example, quartz. Quartz says variable. And so what does that mean? All of these pictures, by the way, on this slide are all quartz. And that's what makes it very hard to identify quartz by the color alone. So it's not a good way to identify minerals. Sulfur, yeah, you could tell sulfur is usually yellow. But something like quartz is very hard to identify by color. This one up here in the top left is, they call that your garden variety quartz. That's like your normal quartz, this clear. This one over here in the top right is called milky quartz. It's got that sort of milky white color. Down here you've got in the bottom left a citrine quartz. It's got a sort of yellowish, amberish color. This one in the bottom middle is called smoky quartz. It's got this grayish black color. And over here you've got rose quartz, which is sort of a light pink color. But again, all of these are quartz. So it's very hard sometimes to identify by color because minerals will come in many colors. And the other thing is you have a lot of minerals that have the same colors. Like there's a lot of clear minerals out there. There's a lot of white minerals out there. And so it's very hard to identify just by color. Luster. Luster is a very good test. And on the back of your reference table, the first column way over on the left-hand side there, they will tell you which minerals are metallic. And there's two groups, metallic luster and non-metallic luster. Most of your minerals, majority of them, are non-metallic. Non-metallic minerals are, and they're broken into subcategories. So a mineral can be non-metallic and then have other categories that classify it. So dull, a dull finish, right? Kind of no shine at all. Earthy, an earthy mineral would look like dried up clay or dirt. Glassy, and this gets a little tricky with glassy. Something like quartz. Right, let me go back to the last slide. This quartz up here in the top left has a glassy look to it, but that does not mean it's metallic. All right, and this is where it can be a little confusing. Students will look at quartz and say, oh, Mr. Rocco, it's shiny. It's a shiny piece of glass. And then right away associate, oh, shiny, that means it must be metallic. In order to be metallic, and that's why I put this here in my notes, it has to look like metal. Like it has to look like, think of aluminum foil. If you take a piece of aluminum foil out of the kitchen drawer and crumple it up, and then look at that aluminum foil under bright light, right? It's got that real metal look to it. It is metal, it's aluminum. So that's what you want to think of when you think of metallic. You want to think of gold, like you had a piece of gold in your hand, or a piece of copper, or a piece of steel. I think of a piece of steel, a piece of aluminum. It has to look like metal. Shiny doesn't necessarily mean metallic. And so that can become very confusing sometimes when students try to identify the luster. It has to look like metal to be metallic. There's not that many metallic minerals out there. And I believe, and I'm not looking at the ESRT as I'm doing this, but on the back of the ESRT, I believe there's only 4 metallics listed up at the top. Fake gold is one of them, pyrite, fool's gold. So majority of those minerals listed on your ESRT are non-metallic. So glassy does not necessarily mean metallic. Glassy is categorized as non-metallic. And that's luster. And again, the definition of luster, I don't know if I mentioned that, is just the way light reflects from the surface, right? You hold that mineral up under bright light. Does it have a metal look to it or a non-metal look? All right, so here's a picture of pyrite. Hard to tell in the picture, but that's fool's gold. It's pyrite, so that would be metallic luster. This is definitely metallic. This is called galena, which is also listed at the top of your ESRT on the back page there. Has a silvery metal look to it, so that's also metallic. Streak. So the streak test is also a very good test. And the reason streak is good compared to color is because streak looks at the chemical composition. Color is just a facade. So again, when you look at quartz, like I showed you before in all those pictures, quartz can come, like I said, clear, white, pink, black, yellow, you name a color, quartz comes in it. That's the outside facade of the piece of quartz. But when you look at the streak of quartz, it's always going to have a white streak. And that's because quartz is made of silicon and oxygen, which happen to be lighter elements. Some elements will always give you a lighter streak, like a white streak. Other elements like iron, Fe, or magnesium, Mg, those are typical elements that give you dark streaks, like dark gray or black streaks. Quartz, because it's made of silicon and oxygen, is going to always be a light streak, no matter what the color on the outside is. So it can have any color on the outside, it's always going to have that white streak. Pyrite, for example. Let me go back and show you pyrite. Pyrite's always going to have that yellowish, goldish color, but when you actually take pyrite and do the streak test, rub it on a plate, it's always going to have a dark streak, a black streak, and that's because it's got iron in it. It's an iron sulfide. All right, and that's what's going to give it that dark streak. So streak is taking the mineral and you rub it against the streak plate, which is a piece of tile porcelain. Again, you probably did this in middle school. You want to use 2 different colored streak plates. So and normally when I do this in lab, we use a white streak plate and a darker streak plate, like a black streak plate. I have I think dark brown streak plates. You want to use a darker streak plate as well because of something like quartz. Because when you rub a mineral like quartz on a white streak plate, it's hard to see, obviously, white against white. And so I usually tell students, rub the mineral on both streak plates. Rub it on a black streak plate and rub it on a white streak plate so that if it's a white streak, you can see it on a dark surface. Right? So that's always important. So streak is just the color of the powder, what it looks like after you've rubbed it on the plate. Again, galena, that was a picture I showed you a minute ago, has a grayish silver color, but when you put it on a streak plate and you rub it against the streak, the powder is a black streak. All right, again, because it's got those darker elements inside it. Hardness. So hardness is the resistance of a mineral to being scratched. Can it be scratched or can it scratch other objects? Mineral's resistance to being scratched is hardness. And there is a hardness scale. These are 10 very common minerals. And again, there's over 3,000, but these are the 10 they use for this scale. It's called the Mohs hardness scale, M-O-H, made up by the scientist Moh, who created this scale. I forget when, a long time ago. Anyway, this is a scale going from 1 to 10. So minerals are classified anywhere between 1 to 10, and can be halves as well. Like you could have a 3.5 or a 2.5. And these are some common objects over here on this side that you would use when you perform the hardness test. Especially the one you're going to use very often is the glass. This is the one you use most often. Glass has a hardness of 5.5. And so if a mineral is harder than glass, take these up here, 6, 7, 8, 9, 10. Orthoclase, feldspar, quartz is a 7, topaz is 8, corundum is 9, and a diamond, of course, is 10. So anything 6 through 10, because it's a higher number than glass, can scratch glass. So the rule is a higher number scratches a lower number, right? Which makes sense because that means it's harder. So something harder can scratch something softer. So any of these minerals up here, quartz, topaz, diamond, can scratch glass. Will leave a cut on the piece of glass. If it's softer than glass, like talc, gypsum, calcite, fluorite, and apatite, these 5, because they're not as hard as glass, when you rub them against a glass plate, and that's how you do the hardness test, rub it against the glass, it won't scratch, right? Talc won't be able to scratch. Now, you have to be also very careful with the hardness test, because this is comes up all the time when students are doing this in lab. Talc, because it's extremely soft, and let's say this is your glass plate, and a student will rub the talc against the glass, the talc will leave powder on the glass. And so many times a student will get fooled and say, oh, Mr. Rocco, the talc scratched the glass. That's weird. And I'm like, did it scratch it or just rub off onto the glass and leave a white streak of powder? You want to obviously have the glass on a table. Never do the glass test in your hand in case the glass breaks. So you want to have it sitting on a table. You've got, that's a really big piece of glass. But anyway, let's say you have your piece of glass. You want to hold the glass with 2 fingers and you want to rub against it, but you want to, as you're rubbing the mineral on the glass, you want to listen too, because you want to hear that annoying cut glass sound. Talc will not do that. You could keep rubbing back and forth and it'll leave a powder, that's for sure, but it will not actually physically cut the glass. You won't hear that annoying, nails against a chalkboard sound. So be very careful when you're using these softer minerals on a glass plate. You want to hear that cut glass sound. Make sure it's just not a powder. Sometimes I tell students, I wouldn't use your finger, but take, in case it did cut and you don't want to get little shavings of glass in your finger, take a piece of paper towel, wipe it on the glass plate to see, did it actually cut the glass, or is that powder that just now wipes right off? So you'd grab a piece of paper towel and just rub the glass plate to see if it actually made a good scratch. Quartz, topaz, corundum, these minerals up here are definitely going to leave a nice deep scratch, and you're going to hear that. As soon as you take a piece of quartz and rub it against a glass plate, you'll hear that. So the way this works is, let's say I had a mineral. I want to know, I want to try to come up with its hardness. You want to use the glass. That would be the first tool I would use. So you're going to rub it against the glass plate. Let's say you take a mineral and it doesn't scratch glass. So right away, as soon as I know, all right, it doesn't scratch glass, and glass is 5.5, that means it's got to be lower than 5.5. It's down here. The next thing I want to do, because I don't want to just say, well, it could be anywhere from a 1 to a 5. I want to keep narrowing down my hardness scale. So if it doesn't scratch glass, I know it's soft. Then I might use one of these tools, especially the fingernail would be the next thing I would use. Your fingernail is about 2.5. So you would take your fingernail and try to see if your fingernail can scratch it. I always fascinated when I watch students do this in lab. They'll take the mineral and try to scratch their fingernail, which you could do, but you really do it the other way around. you take your fingernail and see if your fingernail will put a scratch or even a groove into the mineral. So again, let's say it didn't scratch glass. That means it's 1 to 5. Then you take your fingernail. Let's say your fingernail can put a nice easy groove. You're trying to scratch it with your fingernail and it grooves into it, cuts into it. That means it's got to be less than 2.5, right? Because if your fingernail can cut into it, it's softer than your fingernail. So that means you're down to a 1 or a 2, probably talc or gypsum. And that's about as far as you need to get. Do you have to get down to it's a 1 or it's a 2? No. As long as you give it like a 2-number range, you're usually going to be able to identify that mineral. So doesn't scratch glass, try the fingernail. If your fingernail can scratch it, it's a 1 or 2. Now let's say it doesn't scratch glass again, it's a 1 to 5, but let's say this time you try to scratch it with your fingernail and your fingernail can't scratch it. That means it's got to be harder than 2.5, but less than 5.5. So now you're in the 3, to 4 to maybe 5 range. The next thing you could try would be the penny. You would take just a regular penny and see rub the penny on it. If a penny can put a scratch on it, but your fingernail can't, right? That means it's harder than your fingernail, but softer than a penny. That would put it into the calcite range, right? That's a pretty easy one. So if a penny can scratch it, but your fingernail can't scratch it, it's harder than a fingernail, but softer than a penny, it's got to be a 3. If your fingernail can't scratch it and the penny can't scratch it, so now you take the penny and rub it against the mineral. So it won't scratch glass, but the penny won't scratch it either. That means it's got to be higher than a penny, but lower than glass. It's probably in this 4 or 5 range. All right, and that's essentially the way you do it. If it scratches glass, obviously it's higher than a 5.5. It's like a 6 or a 7. On the back of the reference table, the minerals, they only go up to 7. So when you ever use minerals and they come out scratching glass, you're just going to call it automatically 6-7. There's no 8s, 9s, and 10s. So whenever I do this lab, hands-on, there's no topaz, there's no corundum, and I'm certainly not giving students diamonds because they wouldn't be sitting there very long. They'd be in my hands, by the way. So I don't use 8, 9s, and 10s. I use anything in the 6, 7 range. So if it does cut glass, you're going to call it 6-7. All right, how the mineral breaks, again, is affected by, and this is the number one thing right here, and I talked about that before, how the atoms are arranged. Remember I talked about graphite versus diamond. Graphite is soft and a diamond is hard. It's what they call the internal arrangement of atoms. That comes up often on a Regents question. They'll say what affects hardness, what affects the shape of the crystal, what affects whether it has cleavage or fracture, how it breaks. It's how the atoms are arranged internally, right? Internally, that you can't see microscopically. If a mineral breaks along smooth, flat surfaces, right, smooth edges, right angles, if you look at some of these pictures down here, you can see that. Looks like a parallelogram, right? Take a math class, you get parallelograms or a rhombus, or it's got a cube shape to it, or a triangular shape to it. Anytime you get these smooth, flat surfaces, that's what they call cleavage. So cleavage is if it breaks along smooth, you're looking for smooth edges, which is not always easy to see. I will say that straight out. Students sometimes will have a hard time seeing if a mineral is breaking with these smooth, flat sides. Some minerals don't show it as well as others. Some are like a clear, dead giveaway. You can easily see that it has smooth, flat sides, and right away a student say, yep, that definitely has cleavage. Some minerals, especially when we're using these in lab, students will have a hard time telling, and that's perfectly normal. And I tell students, it's okay, bring the mineral up to me and let's take a look at it. And you might see some of the mineral shows the cleavage, and other parts of the mineral it's kind of rough and jagged, shows fracture. And that is normal with minerals. Some minerals will exhibit both. And if you look them up in like a mineralogy book, like a science book on minerals, you'll see it'll say shows cleavage, shows fracture, which is can be common for some minerals. At the high school level, I try to stick with minerals that either definitely show cleavage, or the opposite, which is called fracture. And let me show you some examples. So this is galena, which again, and I took this right off the ESRT. So it has a hardness of 2.5. This little check mark, and it's on your ESRT. There's a column on the left. There's a line that goes down like this. and there's check marks. If it's on the left side, that shows cleavage. If it's on the right side, it shows fracture. And you'll see most of the minerals on the back of your ESRT, I believe the check marks are on the left. That means a lot of minerals have cleavage. A few do have fracture. This one has cleavage. And you can see this looks like little tiny cubes all kind of put together. But you can see the smooth flat sides. I'll put X's on them. So here's one here. Here's a flat side here. Here. I mean, these are all little flat sides. These are all little cubes like mashed together. So this does have a good example actually of cleavage. Smooth flat sides there. And you can see right angles. Like here's a right angle. Here's a right angle. They call that cubic cleavage. Cubic. See how it makes right angles here like a cube? And they'll say it in the one of the columns on the back of the SRT, they'll say distinguishing characteristic. And students will say, what do they mean by that? It's one or two things in that mineral that make it stand out from other minerals. And you can see right here, and I cut and paste this off the ESRT, galena has cubic cleavage. It also has a grayish black streak. They tell you what it's used for. It's very, very heavy. The density, it says 7.6. That's really heavy. It's used for batteries, and it's an ore. An ore is something that they mine out of the earth and then manufacture into other products. So galena is used for lead products, and it's used in your batteries. And then they give you the composition PBS, which means lead sulfide. And then you've got the name of the mineral. And so that's a good example of cleavage. Here's an excellent example. This is calcite. And they will tell you, again, this column, which is in your reference table, distinguishing characteristics, it'll say, has rhombohedral cleavage, which a rhombus is, right, a parallelogram shape to it, although I believe a rhombus is all the sides are equal. You might not see that. I don't like that they call it rhombohedral, but I would call it's a parallelogram. And you can see the parallelogram shape right there. So that's what you're looking for in something like a calcite. It's got that parallelogram. And these are all good examples. So you got flat side, flat side, flat side. These are all good examples of cleavage face. They call them faces. So each of these is a face. This is a face. This is a face. This is a face. These are all faces. You can see the hardness is 3. Again, the check mark is on the left side of that line. So that means it has the cleavage. They show you that it's variable. There's that. I was talking about color. It means calcite can come in a lot of different colors. What it's used for, cement and lime. There's its composition. It's called a calcium carbonate. It's got calcium is Ca, and anything that has CO3 in it, CO3 is a carbonate. It's got carbon with 3 oxygens locked together. Anyway, so that's calcite. Good example of cleavage. If it doesn't have cleavage, it's going to have fracture. Fracture is when it breaks unevenly, right? Just as if someone breaks their wrist or fractures their arm or fractures their ankle, right? The bone broke kind of jagged. There's no nice flat sides. And so it's an uneven break. So fracture is when things break unevenly. And these are 3 examples of how a mineral will break unevenly. Earthy, hematite. Hematite has this reddish brown, it looks like just a chunk of red-brown clay that got hardened into a mineral, and that's really what it is. If you took this hematite and then just kind of smacked it with a hammer, it's just going to break apart into crumbles. It's going to kind of fall apart. So that's earthy fracture. Fibrous fracture. Fibrous is going to be splintery, so it's going to make these little tiny splinters, just so if you get a splinter in your finger. That's fibrous. And then you have what's called conchoidal. Conchoidal fracture has a scooped effect to it. This is a rock, obsidian, which is that volcanic rock. It has a black, shiny glass look to it. Obsidian has these scooped out. It's like if you took a brand new, fresh half gallon of ice cream and you took a nice ice cream scoop and then took one big swipe out of the top of the ice cream, and you get that scooped effect. That's called conchoidal fracture. Or clamshell. I usually refer to that. If you took a shell off the beach and flip it over and you got that scooped effect on the inside of the clamshell. So that's what they call conchoidal fracture. So you've got earthy, fibrous, and conchoidal. Most common one's going to be this earthy one. Hematite will do this. Sulfur. If you took a piece of that bright yellow rotten egg smell sulfur and you took sulfur and smack it with a hammer, it's going to break apart and just crumble. So things like hematite and sulfur, they're going to have fracture. They're not going to have smooth, flat sides when they break. And then the last physical test is called specific gravity. This one really isn't one you would do any kind of test on. It's really the same thing as density. The only difference is you don't put units. So if you had a mineral, let's say, that has a density of 3 grams per cubic centimeter, drop the grams per cubic centimeter, you would just say it has a specific gravity of 3. So it's the same number, just drop the g/cm cubed. Most of your rocks and minerals tend to have densities of around 3 grams per cubic centimeter, so their specific gravity is 3. With the exception of gold. Now, if you have pure gold is very dense, 20 grams per cubic centimeter. So pure gold is about 7 times more dense than most of your common rocks and minerals on Earth. Extremely dense. So it has a specific gravity of 20. You can do a test with the specific gravity. It's actually called the Heft test. H-E-F-T. Heft test is you would have to have 2 minerals, let's say a mineral A and mineral B. They'd have to be pretty close to the same size, if not the same size. You would put one in each hand and just kind of like you could feel the weight compared A to B. So you kind of put A in one hand, B in the other. Again, they have to be about the same size, and using your hands as like a scale, right, to be able to tell which one feels heavier. And that's one way you can compare minerals. They call it the Heft test to compare the weight, which of course sometimes I'll say to students, heft, if you add a Y on the end, you get Hefty, which is I believe, garbage bag company, right? Hefty. And so that's where that whole Hefty came from, when the Heft test for weight, like how strong, right? So there you go, little trivia. Pure gold. So this is pure gold. Again, it has a specific gravity of 20, which is very, very heavy, very dense. And gold, this is prices of gold. Gold prices are interesting. They'll fluctuate with the market. So I have that link on there. I think I had that up there for students to see what the price of gold is, and they'll project it where it's going. But anyway, so you can see this is actually, you click on this website I go to, this APMEX.com, and they'll give you the current gold price per ounce. So per ounce of gold, that's pretty high right now. So gold is at $1,734.20 an ounce, which is pretty high. But that'll fluctuate day to day, and you can see what it goes up or down. Went up a couple bucks. Yeah, kind of interesting. Gold will go with the market. So that's the price of gold right now, $1,700 an ounce, which is a lot. And one more test. Sorry, acid test. So hydrochloric acid, very dilute. Because they'll say, what do you mean by dilute? Dilute means it's mostly water. And so I do this in lab as well. I have a bottle of this hydrochloric acid. It's 90% of it, though, is water, and only 10% of it is hydrochloric acid. You would not want to use pure hydrochloric acid. You'll burn right through your skin, and you would not like that feeling. So you're going to use this very, very dilute hydrochloric acid. It's mixed with 90% water, but just enough acid that when you drop it on certain minerals, particularly calcite, and again, you might have done this in middle school, it'll, what they call bubble, or the word they use is effervesce. I love that word, effervesce. It's kind of cool. 7-Up or Sprite. If you ever take a fresh 2 liter of, let's say, Sprite, and you put it into a glass, and then you add some, the ice cubes in there, and you get that fizzle coming off, the little bubbles coming off the 7-Up or the Sprite. Even Coke will do it too, but that's called effervesce, or it bubbles. And so that's what's going to happen when you drop this very dilute hydrochloric acid on a piece of calcite. You'll get this bubbling coming off there. So that's like a very specific test, the acid test, that works with certain minerals. Calcite, and again, this is like cut and paste off the ESRT. Not only did it have that rhombohedral cleavage, so it had that parallelogram shape, but it also says it on the ESRT, bubbles with acid. Calcite will bubble dropping the acid straight onto the mineral. There's another one on there besides calcite on the back of ESRT, dolomite. Dolomite, it also says bubbles, but it's not directly on the mineral. You have to powder the mineral. So you have to crush dolomite into a powder and then drop the acid on the powder of dolomite, and it will bubble. And I believe it does say that on the back of the ESRT for dolomite. But both of those will, and that's this carbonate. It's got that CO3, carbon oxygen 3 in there. That's what's causing it to have that bubble effect. So the acid test, it's a good test to a certain extent. I don't classify it, it's good for calcite, but the problem is with 3,000 plus minerals, it's not going to help you with the other 2,900 plus minerals out there. So it's not, I don't classify it as a good test. Yes, it's good for calcite, but that's about it, and dolomite, but it's not going to help you with the rest of the minerals. So in terms of, is it a good test? I would say no, only because it doesn't help you. Like your good tests, again, are going to be your streak test, your hardness test, your luster test, you know, whether it has cleavage or fracture. Those are probably going to be your best tests. Streak, hardness, luster, cleavage, fracture. Those are your better tests. Acid, again, works for this, but that's about it. All right, I think I'm going to stop there for the first video, and then I'm going to pick this up in a second video to talk about how a mineral gets formed, but that'll be in the next video. And I will talk to you soon.